For the class number 24th, the 6th of April 2020, I'm gonna explain you about the super assignment of this class a little bit before we proceed to the next structural element, which is the plate bending cases. So what are in this gift box? So inside this gift box, we are going to work on the plane elements. Basically, we're gonna do a lot of Q and we're gonna do some with T element. And the code for the Q and T elements are already available on the Google Drive. I uploaded that for you. You have access to all of them, and if you had time, you might have done something with all these resources already. I hope so. If you haven't done, then you will be doing it very soon, because it turns out to be the homework, and this is the super assignment. So first of all, I would like you to modify the code. I developed it for you in the class, and then the thickness of the plane element does not need to be just 1 unit. I just said that over here. The thing is that when we formulate everything, actually the integration we did, if you recall, we figure out the strain, we figure out everything in the plane, right? So we come up with the energy, strain energy, but then we need to integrate over the volume. And you saw something, I think you still recall that the integration we had was with respect to the x and the y, right? You have two integral with respect to x and y. So where is the integral in the C domain? That integral in the C domain is over the thickness of the plane element, and without doing anything, without multiplying with anything, that means you are working with the plane problem of which the thickness is equal to 1 unit. Okay. So that's the code that we have so far. I would like you to, this is very easy to do, so just modify the code and make it possible to handle the case where you have less than or greater than 1 unit. That depends. If you are doing centimeters, then you might have a few centimeters for the plate. If you have meter, then you have 0.00 something meter. Whatever, but we need something which is not 1 unit thickness. Okay, so the first one is checked. It is quite simple to do. Now let's move on. For the second point, I would like you to find the spurious mode, or in fact I should call it the zero energy mode. Zero energy mode associated with quite many things, right? To the rigid body, rigid body could be the rigid body translation and rigid body rotation. How does rigid body translation looks like? Let's see. I move this thing here, so I get some more space. Okay. So the rigid body translation, you start with the element here. If you don't have the boundary condition, you will end up with the translation. So you can have translation in x, in y, in both directions. You can also have the rigid body rotation. So translates already, then you go to rotation. So it could turn out to be this picture. And it could be or combined. It's a combinations of multi-mode combinations. So you have the X, Y, and rotation embedded in one eigenvector. So this is the first kind of zero energy mode. The second kind of zero energy mode is associated with the so-called outclassing. The outclassing is actually the mode that does not need energy to deform. This is about the deformation of the element, but these deformations are not causing the energy. So you will come across the outclassing modes as well. So let me just give you the idea how we come across, how we proceed with this number 2. So in order to do all of this, you will just come here. The code here will be given to you. Actually, the code was modified just a little bit from the class number 23. And in that class number 23, I add this point here, which was the rigidity matrix that is changing with the element. Individual element could have the different elastic modulus and Poisson ratio. Let's say the elastic property, and that makes it possible for you to analyze the composite material. For example, the reinforced concrete members. You could have steel reinforcement at the same time with the concrete material, in the combination. So as you can prescribe element by element, point by one by one, that this one is going to be this material, this one is going to be the other, and you have the flexibility rather than just analyzing only one kind of material. Now we had that flexibility. Actually, if I could, I think I plotted in the figures. I don't remember. Actually, this figure, the reason why you cannot see the stress actually in this line here shouldn't blend with the outside. The point is that I apply the stress smoothing, and stress in steel and stress in concrete shouldn't be smoothened. Right? They are two different materials. So very high stress in steel should not come bother the figures you obtain in the concrete. And here's the thing. I don't want to do much more than this extent of the code. So if I don't incorporate the stresses in steel to the concrete stress smoothing, then the rate will not dissipate out of this boundary, right? Because in reality, the stress in steel shouldn't influence anything about the pattern or the distribution. It shouldn't be a part of that least square operation. But anyway, we actually can plot the unsmoothened stress if you want. It is very simple to do, but the point is that you're gonna need to modify the code also in order to get that done. Alright, but you can see that in this band, which is the location of the steel, you find a very high tensile stress, whereas in concrete, you do not have as much stress, and you have compressive stress. This is a component of stress in the x direction. So this is sigma xx. If you look at the strain will not exhibit the jump like stress. What is the reason? The reason is very simple. Because we have the strain compatibility over the cross section, you expect that your continuum, which is very simple like this for the beam problem or the flexure problem, we expect the plane sections remain planes, even though this is not that slender beam, but still at the middle part here, where you do not expect the shear stress in this area, so you have just a pure bending effect within this zone between two point loads, and that's why the plane sections remain planes is gonna work, and strain will be distributing in the by following that concept. But when you get strain and multiply by elastic modulus, which is very high for steel, about roughly 10 times of concrete, nearby concrete, so you will find that the stress in steel is higher than stress in concrete. And when we plot stress, we can see the concentration of the stress in here. And the code in the class number 23 didn't show that, because it just multiplied by the same rigidity matrix. That I'm going to show you what happened in this version, which is just a little different from the previous version. So we are at the topmost. We can see that we incorporate the DMAT in here. Every time we change from one element to another, we are changing the DMAT, right? And then we finish, we solve, we get displacement solution. Having that done, having that solved, we come to the stress and strain recovery routine. So the strain recovery routine is not going to be bothered by the rigidity matrix, whereas the stress will be, right? So the rigidity matrix, as it changes as the element numbers change, I put it here, so it has to be re-established, right? You understand this point? Because every time we compute the stiffness matrix, before, when we find the K, we got to keep changing the DMAT, because EMOD and Poisson ratio could be different for element I. Now when we back calculate in order to find the stress, then you will need to again call this and recompute all of this. So when you multiply by the DMAT, which is going on over here, we will be getting the stress associated with that given element. Okay, 1 second. And now let's see. So this is the part that I just want to highlight, that I made, just add this part in, and just that it works and it shows stress as it should be. Okay, so this is the point that I left off in the last class, that just need to add this thing, only thing. Okay, right. Then I think I can jump back to the screen over here. So the code that you just saw, I'm not sure, but I might have uploaded it already if I haven't done that yet, the latest update, then you just add this update by yourself. It is not difficult. It is just a few lines of code, so you don't need to get that latest, very latest update. The part that I uploaded already can do pretty much everything already. So, right, you don't need to wait. Tonight, if you cannot sleep, then you just grab the code and try to do all of this. So, modify the code in number 1 and number 2, find spurious modes. How many spurious modes I want from you? I have 6 spurious modes for this assignment: Q4, Q8, Q9. Q4, Q8, Q9, they are the full integration, fully integrated. Maybe I call it this way, from full integration. Whereas these are from reduced integration. And in the input file, I put the possibility for you to change the number of integration point. So you can change to 1 point, 2 point, 3 points. It's up to the element that we are dealing with. Okay, so 2 point, 3 point, 3 point, whereas this one 1, 2, and 2. In order to find spurious mode, I cover in the maybe the last or in the class number 22 already, that we are going to find the eigen value of the matrix. And over here, if we have the k, right, just recall times u was supposed to be in the global coordinates, multiply, and then you get the f, and f is a false vector. And for the eigenvalue problem, you have 0 false. You are looking for the modes that's not associated, that is associated with the zero energy. Zero energy, well, you have the 0 false. So this equation will be possible. If we don't want the u to be 0, then you need to find the k such that the determinant is equal to be 0. So actually you can come to this one. I bring you to the desktop screen. So you have the dead determinant of the k equals to 0. Maybe I can just make something like this for you. I just come up with some assume values in the matrix. So make the A be this 2 by 2 matrix, and then B comma C is equal to eigenvalue of A, and there it is. You have 2 matrices B and C. The matrix B includes the eigenvectors. So you have 2 eigenvectors that are orthogonal to each other. What is the orthogonality? You learn a lot from the dynamic class already. And actually all of these, if you work on this in the dynamic problem, if you want to find the fundamental frequency of the structure, then you just use the command like this. Okay, so you get the eigenvectors, and you also get the eigenvalue out from here. Alright, vector and eigenvalues. Eigenvalues will be in the matrix, and the values will be in the orthogonal line of the matrix. So you'll be using this in order to find the eigenvectors. Once you get eigenvector, what's next? So each eigenvector is gonna be associated with the eigenmode. So you have x and x. This is for just 2 by 2 matrix. If you imagine for the case that you deal with, you have the Q4, that you are going to have the 8 by 1, right? You have in total 8 rows, because at each node you have 2 degrees of freedom, and you have 4 nodes, so you have 8 degrees of freedom. 8 degrees of freedom is going to make your stiffness matrix for an individual element being just 8 by 8 matrix. And that 8 by 8 matrix is going to, we're going to find the eigenvalues, eigenvector out of it, and the eigenvector will be used, and you can take it one at a time. So, okay, one column at a time for your consideration. So you get 8 by 1 coming out of your eigenvector matrix over here. Okay, you get it. Oh, sorry, I didn't switch the screen back. Sorry. Okay, so it's gonna look like this. Sorry, I should stick with this screen. What is the meaning in this eigenvector? So you have the elements over here, and you know which one is the first node. That depends on how you put the node numbering to them. And you have these 8 figures. These 8 figures, the first one is the x displacement, second one y displacement at node number 1, x and y at number 2, x and y at number 3, and x and y number 4. So in total you have 8 numbers. If you extend to the what is it, Q8, you are going to have 8 multiplied by 2, which is 16 numbers. So one eigenvector has 16. One eigenvector has 16 displacement, right? And all those 16 displacements will be added to your coordinate. So your coordinate used to be x1, y1. You're gonna update your coordinate. I would like you to first plot this blue line, the original coordinate, and then if the zero energy mode is not going too far away from the original element, then please include. But if it is so far away, then you might not be able to include. For example, the point is that when the element is not restrained by the degree of freedom, you end up having the rigid body translation. And rigid body translation, the solution is not unique. So you can translate just a little bit. You can translate like very far away from the original element. This is possible because you do not have the boundary, the support, right? What you do is that you get the original coordinates x and y, 1, 2, 3, 4, and then you add it up with the figures you obtain from the eigenvector. So So you get number from eigenvector y1 plus e2. If I call this one e1, e2, e3 all the way to e whatever, and then this guy turns out to be x2 plus e3, and then y2 plus e4, and so on and so forth for other nodes. So you get the new coordinates of your nodal points. Alright, you only get the nodal points coordinate, the updated nodal point coordinates, but still it doesn't give us this picture, the picture like this. I actually want you to end up with this picture. And how do we get this picture? This picture draws the perimeter of the element and also the material line and the inside. So perimeter, we have all four sides, but all four sides might not be just a straight line, right? Because it can deform. If we talk about Q4, of course, you must end up with a straight line because the interpolation function is just a linear interpolation, and you cannot get anything which is non-linear going on there because x and y will be interpolated linearly. But for Q8 and Q9, it is possible for us to end up with the curvy line, and that's just a quadratic function. You cannot go more than that because your shape function is just as far as the just the quadratic interpolation function. Okay, so I need you to draw these lines, all these lines. This is quite easy to draw the line on the border, the boundary of the element. Okay, but actually it is not that difficult in order to draw the line in between. So these lines are going to be drawn such that we can see how the deformation, how the change of how the strain, well, you can idealize, not idealize, you can visualize the strain in this particular element by drawing these material lines. So let's take a look at the numerical coordinate of the element, of the quadrilateral element. I draw in the yellow line here, they are the material line, and I break the material lines into some finite number. So for example, this line, well, we have broken it down into 4 equal size, and this is -1, this is +1, so this is 0.25, 0.25, all are 0.25. Likewise, for the plus, for the positive side, you get like 0.25 4 times. Okay. So each line here, for example, if I'm gonna define this line is what? It is the C equals to 0.25. So as the C is equals to 0.25, you can get many lines along this, get many points along this straight line. So I would like you to break it down into 20 equal segments. That means eta is going to be -1 equals to be what else? 20 and -0.9, -0.8, and up to 0 and up to 1.0. So you are having in total 21 points. 21 points, 21 coordinates. So if we talk about the C and eta coordinates, C is 0.25, eta equals to minus 1.0. C is 0.25 still, because C is not going to change, minus 0.9. 0.25 minus 0.8, then keep going like that until 1.0. You get these sets of coordinates. And this is one line, only one line. And then you move over to the next line. The next line, what is the difference? The difference will be only eta is going to be the same sets. The C is going to change from 0.25 to 0.5, and that's it. And then you go to C equals to 0.75, C equals to 1.0. So the operation is going to be the line like this, from the first to the very last. Done. And then you change your operation into the horizontal line. Okay. Now, it is not just that, because we are talking about things here. This is in the local coordinates. We need to draw the line in xy coordinate, or in the physical coordinates. So we are not finished just there, right? How do we get that? We need the coordinates of xy. We don't need the coordinate of C and eta. And in order to convert all of these into the xy coordinate, x is approximated by the C and eta function of C and eta, right? Which is equals to the summation with ugly summation sign. Summation from I equals to 1 to n. Basically, this n is the E type. So we talk about Q4. It conducts the summation for 4 times, because you have just 4 shape functions, right? You have 4 approximations. What else? X is going to be approximated using the nodal point x value and the shape function phi. The shape function phi I is a function of C and eta. And that is it. Now you get the x coordinate. This x coordinate is associated with all of these. C and eta at the prescribed location. Guys, just this plot is gonna take you a while. And especially if you do it by yourself, it's gonna take you a while. I can write the code for you. I can get it done in roughly 15 minutes. But to do it the first time by your own, okay, the brain cell is gonna work, and that's gonna create a good thing into your brain. It's gonna extract a lot of brain juice coming out. So doing this for the first time is not going to be easy. But if you can do it for some time in your life, in the next time, you'll be able to do the thing that is as difficult as this one. But if this is not going to be achieved by you this time, you will not be able to do anything that is more difficult than just this for your lifetime. Okay? So it's gonna take your time, but you have time. So please take your time to do homework. Right. Now we get the x, the y will be carried out in the same fashion. So actually I should not have to explain like this. So summation, you can expect what's gonna happen. E type and then yi, phi I, c and eta. This part here is going to be the same. The c and eta, they are coming along with the subscript. Difficult to find place. J, okay. Now you are having quite this is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So J is the number that you are working on. You are trying to plot this. J equals to 1, this, J equals to 2, and so on, so forth. So you plug in the fixed value of C and eta associated with the J. And this C and eta will be going to the shape function. So you plug them into the shape function. Which shape function? X for node number 1 multiplied by shape function number 1 evaluated at C, J, eta J plus, so well, if I expand it out, I'm gonna have the X node number 1 multiplied by the shape function number 1 evaluated at C, J, eta J. So if this one is for example a quarter of 1 minus C and 1 minus eta, the C will turn out to be Cj, eta will turn out to be zeta J. So you just go and look up for the shape function plus X coordinate of node number 2 multiplied by the shape function number 2 Cj and eta J up to X n phi n, that thing. And all of these are gonna need a good architecture in just the plot alone. But think of it, think about it. It's not beyond your capacity. You have the capacity embedded. The thing is that the different people, the only difference are the tolerance level. If you can tolerate the pain and you still struggle, you don't give up, then you will achieve. You'll be able to make all of this possible, right? If you give up, you say, okay, I cannot do, then you cannot do. And the human beings are very easy to get spoiled by the giving up for all kind of things. Once you give up doing something, it is very likely that you are going to give up doing some other things, and that's going to turn you to be a loser at one point. So if you don't want to be, don't give up. If you don't understand, this is available on YouTube. Rewind and try to listen carefully, and then you will get why it works this way. If it is not possible to understand, even though you're rewinding this for several times on YouTube, then let me know. We're gonna have some sort of Zoom session such that we can talk and let's figure out what is too difficult for you to do. But this sort of thing is the same kind of homework I had when I was studying. So Professor Baker just told the class to draw the material line, and he didn't give this much detail, that the X will be drawn this way, the Y will be drawn this way, and so on. Okay, so you will end up with, after this procedure, you are going to end up with X1, Y1. We are talking about just one line, guys. This is just one material line that you have a bunch xj, yj, and x21, y21. You have 21 coordinates. It is possible to draw one single line, and that's it. And then you change. So the change operation like this gonna happen for how many times? 9 times, because constant value of x. You have 1, 2, 3, 4, 5, 6, 7, 8, 9. If you break them into the interval of 0.25 from each other, and 9 times as well for the horizontal line. Horizontal line in computational coordinate, but it's not going to be horizontal line or straight line like the yellow one you saw when we come and talk about the physical coordinates. So each individual points are going to, well, map like this. For example, this point here might be mapping to this one here. This point here is going to map like this. Something in between here is going to map onto this thing, just like this. So it constitutes one line, and you're done with one line. Now you hold off first, otherwise your line is going to jump there if you don't hold off. Okay, so you guys, you need to hold off so it does not connect the dot from one end to the beginning point like that. Hold off, then you start the new line, and then hold on, and then plot to this point, hold off again. Yeah, just check the hold off, hold on a little bit, otherwise you're gonna get the zigzag like this. Done in one direction, go to the next direction. Okay, it is bearable, it's not too difficult for you, but you guys spend time thinking, doing this. It helps improve your brain, and this is actually very good when you are old. So when you are old, really old, and you do not want to suffer from dementia, you don't want to have Alzheimer, you come back, watch this video and listen to this homework, and try to do this homework when you are somewhere around 70s, which is not far away from the death, of course, at that time, and try to do this homework so you will not bump into dementia. Your brain is going to exercise and you'll be good. Then you get this checked. Plot out spurious modes by drawing material line in the physical domain associated with the following line in local coordinates. If you develop the code for one time to plot the spurious mode for any of these, okay, then the remaining 6 are going to be easy. Just get the first one done, right? The remainings are going to be easy for you. Okay. What else? So I asked you to plot spurious mode. I have by the way, there's a good reason to call this one super assignment, because if we look into the Q4 contains 8 degrees of freedom. Your matrix is 8 by 8. How many eigenvalues do you have? If your Q4 element is not restrained at all, I mean you do not have the boundary condition at all, you are going to end up with 8 eigenmodes. Okay, you will have that many. 8 eigenmodes. The eigenvalue might repeat. You might get the repeating modes. If you have the reduced integration elements, you will end up with more zero energy, more zero strain modes than the full integration. So what I imply is that, let me erase this out. For Q4, you have 8 figures to plot. You can put like the subplot figures in one A4. You don't need to put like one figure, one mode in one A4. And but you are not, by the way, you are not going to submit homework through the hard copy submission. That means you are going to make PDF, and then I don't want you to submit directly to me. It should be to Hang. Let me check. Okay. Homework will be submitted to hẳn lý hẹn dot h90 at gmail.com. Okay, so you can fill her inbox. Don't dump to my inbox. I don't want to forward to her. So submit to her, and as soon as something dirty happens again, then she's gonna forward that to me. That's how it's gonna work. Okay, so 8 figures. This one 16, right? This one 18 figures. 8, 16, and 18. So in total, how many? Yeah, you just sum them up. This is just this to this 34 plus 8. Yeah, 40 something figures, and it should be fully automated. If you don't make this code, if you still rely on some manual operations, that's going to be quite painful. So you're going to see a lot. You're going to see rigid body, rotation, rigid body, translation, sometimes translation in X and Y combined, sometimes translation combined with rotation. Okay, you're going to see all kinds of these things. And you are going to see the outclassing when we talked about the reduced integration. Okay, so you're going to see clearly about the outclassing, that it gives you, zero energy. It requires zero energy, but you can find that it looks like it has a strain, right? I shouldn't say zero strain, but it is zero strain energy. Okay, to be precise, you have strain, but strain energy turns out to be zero. That is the shape, very particular shape of deformation that does not need the external force. So Q4 is going to show the outclassing this way. Q8, Q9 is going to show something like that. Then what else? To show off this, then I would like you to try this as well. When we have zero energy mode, previously that includes the rigid body modes, and we know that in the static problem. For the dynamic, you will not have that problem, because finally the inertia part is going to help equilibrate the system without the boundary conditions. Okay, without the support, the inertia is going to produce that inertia force that balance with the externally applied force. But in the static system, if you have applied force and without the boundary conditions, then it's gonna fly, and then you're gonna get the rigid body mode. Now listen, I know that static problem we're gonna put the boundary condition, so I would like you to do this. Okay, that's it. If I restrain the system against x displacement, y displacement, x displacement, y displacement is not possible, and rotation is not possible. X displacement is here, y displacement is here and there. Well, if you want, this one might not be needed in order to hook it and lock it against the y displacement, but this is introduced in order to prevent this rectangle from rotation. If you do not provide this guy, then this rectangle is going to just spin around. That's the problem, and that's why it is introduced. So for now, when we introduce the degree of freedom like this, we are going to we still can get the rigid body modes. If you use the reduced integration, you study into the reduced integration elements, then you'll be able to see that it's gonna deform like this. As long as you allow this to move freely, then you're gonna see the deformation that's pretty much like this, or maybe like this. Okay. If you talk about the Q element, Q8 or Q9, you still need just this many restraints. Q4, you need 3 against 1x against 2y, or maybe against 2x, and you don't have this one. That is also possible. It is not necessary to be just 1x 2y or 2x 1y, as long as you restrain everything against all possible rigid body modes. That is good enough. But my point is about the element type Q4. How many you need? You need 3 rigid body motion to be suppressed. How about Q8? Q8 has the same number of rigid body modes. How about Q9? Also, Q9 has the same number of rigid body modes. So, you enforce the boundary condition in the same way as Q4. You don't need to add this one for the Q8, the Q9. Alright? It is not necessary. And if you accidentally introduce that in, it's gonna suppress your rigid body mode, the zero energy mode or the spurious mode, because it was supposed to go like this, and then you lock this one in the middle, so it is not possible to go as it wished, because at the middle it was supposed to form some curve, alright, and then the other side form the different kind of curve. Okay, so the boundary condition is clear, right? That we do not need too many. We just need to suppress the boundary condition must suppress all rigid body motion. Are you sleepy today? I feel like you are not quite interactive after the dinner. It is like a lullaby, maybe. So what else? The boundary condition must suppress all rigid body motions. Hey, I want to talk about something. Then I want you to do the number 4. I want you to enforce the boundary condition. The way you enforce the boundary condition, don't do Lagrange multiplier. Just use the row and column elimination, and the code I provide for you actually does the row and column elimination over here. So it enforces the boundary conditions. It removes the row, it removes the column. Okay. And at the end over here, instead of solving for the displacement, you have no displacement to solve here. Okay, you just finish the code just here. You get the cases, which is the new one. You clean out some columns, some rows, and you enforce the boundary conditions already. You have only one element. You get these cases, and then you do the eigen value analysis. So you don't need to do this insertion for restraint DOF back into this. Okay, don't. Okay, this is not whatsoever behind this point is useless for this homework. Just get rid of it, and then you will just put the codes or do some modification after this. So from the line number 89, just delete all of them. Delete it out. And the plot, it will be your job to do, because my code just does the plotting in not the best way. I mean, I can just come back here. My code, if I end up with the Q8 elements in my code, I didn't put the point between of along this line, so I will not be able to capture the curve. That is not possible. I will just end up with something like this, because the code just take 1, 2, 3, 4, 5, 6, 7, 8 like this, just 8 points. So why? So it turns out to be pretty much like this. That's what the code I provided you could do, not more. So I leave it to you, okay, to draw the curve for the quadratic interpolation. It takes so much time to explain the homework, and still ongoing. Still need to explain more. Number 5. After we come across the individual element, I would like you to also try multiple elements. And let's make this one how many? 1, 2, 3, 4. Okay, just like this. And you have these many elements. The mode that is easy to occur will be associated with the lower number, the lower value of the eigenvalues. Pretty much like the dynamic course. Frequency, the lower it is, the easier that mode will be excited. And as the frequency gets higher and higher and higher, then you see that the shape is very complicated. You have like many change of curvatures in comparison with the first modes of the building that it produced only just single curvature. Now, I like you to do this for, I think Q4 is enough, only Q4. And you also enforce the boundary condition to this structure. Actually, it is nothing, and we want to get the eigenmodes. So you'll be able to see the zero energy deformation out of this structure. Okay. What is the size? You might ask, what should be the element size? So the element size and properties. I need the hx equals to hy equals to 2.0. Okay, this is the unit, 2.0 unit. E mod elastic modulus, I just call it just one single material is equal to 100. Poisson ratio equals to 0.2. That should be enough. Thickness, because you have to thickness, make it 0.05. Okay, enough? Yeah, I think it is enough. 1, 2, 3, 4. No more than this. I will need to say the last thing about due dates. Due on, this is the 6th of April, right? You are going to, well, if this is next week, it is the 13th. Make it 15. It does not need to be in the class, right? Submission 15th of April 2020. Due what time? 8 o'clock. Okay, 8 in the morning. PDF format only. One file only. So it is easier to grade. I want what should be inside in this PDF. I want all source codes. All source code means in the main. The part that you use, the part that I developed it and you didn't touch, do not print out. It's just waste. So mainly I think you're gonna touch the main. The shape functions is also given already in which one? The shape function is in here, Q shape. So you do not need to re-establish the function file anymore. You just use the Q shape that I developed it already and make use of it. Okay, so just plot or just print out the part that you modify, and when you print it out, if you can keep the line number, okay, please I think you have the option to print, let's see, new script, print, and number of print to file preference. Generally the code allows you to do that, but if it does not, maybe you can use the Notepad++. Go look up for this one, Notepad++, freeware. Notepad++ is the editor for the programming, so it knows MATLAB M5 code, it knows Fortran, it knows Pascal, it knows Basic, Visual Basic, it knows Java, all the programming language, you name it, Python. It is the editor, so you can copy all of this and put it in Notepad++, and I think that it is possible to call to request the print you want to no, I put it here, I switch it back to this is the Notepad++. You can go the language and let's see, Octave, Object-C, script. Okay, so it does not know Octave, but it knows MATLAB. So as it knows MATLAB, then I come to the editor and Control A, copy, and then I switch to Notepad++, and there it is. And if we want to print it out, do that. Not in here. There must be the option to include the line number. Okay, it's just a little thing. I think that's the way to include the line number, but word wrap, you can Google for it these days. Okay, so include the line number in your printout, and then it is easy to match your line. And when I want to refer to any activity, like I think the line number 29 of yours is similar to the line number 21 of your friends, then it is easy to do the matching and indicating that you're in trouble. Okay, so print out the code, and if possible, well, you can do it by copy the things, put in Microsoft Word. That is possible also, but include the line number. Just Google up, and if possible, highlight the part that you modify my code. If you add something in, you highlight those lines. If you keep the original, just leave the original like that, and it is easy. Sometimes you just move things around so it doesn't match your friend's code, but if things are moved around, then the execution of the command will not be in order, and that's gonna change the meaning, or if the meaning or the operations or the values might be altered by changing or moving things around. So I would like to see the environment of as well, that okay, this is the main code, and how do you stuff things in. Sivaram said that if we print in Notepad++, it includes the line number also. So great, thank you. Then you can opt for any program to print out, but you're gonna get like if you explain something using the handwriting, you might use iPad and write something, extract into PDF. You might need to connect the file to the code, or the printout is the figures, and then you print the figures into the PDF, and it might come as a separate file from the code you see in the editor. Then you need to merge the PDF into one file. I do not want to get into that 7 or 8 files. Okay, the grading of homework or the exam, you shouldn't annoy, okay, the one who grade. So you think of receiving the email, and in one email you put like several files. I will not ask you to submit the M file, please. I don't want to. Okay, submit only single one PDF file. No matter what you have, you connect all of that in order. Put all of them in order, in the order that you think that someone open it up, which is not yourself, will be able to understand your work as you wish. Because if one cannot understand your work, or I cannot understand it well, then that affects your score. So, okay, only one file. I guess we are on the same page. What is it? Why? My Apple Pencil, what is going on? Okay. So print out the main and graph you have. Actually, this is a good opportunity for you to try to play with the plots. You're gonna need this for your thesis, of course. So plot out the figures. You can have like one A4 and subdivide the plots. Okay, so that is so-called the subplot. And you can do this and have as many. And if you do the Excel plotting, you can hardly control the size of all these plots into like identical pixel size in X and in Y, because you're gonna eyeball and try to adjust the figures in Excel. But if you use MATLAB Octave, use automatic plot function, then you're gonna be able to specify and come up with the precise sizing of each individual plot. You will have figure like this. Some is a rigid body translation, some is a rigid body rotation, and so on. Okay, so this is how the homework will be done, and please start doing it as soon as possible, because it's going to take your time, and you also want to take your time and do it as you cannot go anywhere during this COVID season. You stay in your dormitory and you could be driven crazy. Before you get to that point, this is the best vaccine I can ever give to anybody. So this gonna keep you calm. Stay in the dormitory, right? We need to lock you down and restrain you against the social what we need social distancing, right? So I try to refrain you from social interactions. So you're gonna be in the dormitory or in your house, do all this homework for roughly about 10 days, and that's submission on the 15th of April. I might host the Zoom session sometime. What? Severum vaccines. Oh, okay. It's a vaccine for severum, but it's gotta be a vaccine for you all. It's gonna keep you all calm. You be relaxed and stay home. And keep just doing this and removing bugs. Okay. Now, I think. Oh no, not yet. And if you remember, you must remember. You used to deal with question here for the beam problems. I remember that I used to assign you for a given cross section, given elastic modulus, given Poisson ratio, right? Which homework I don't remember. I never remember anything. My point is that I have not finished this yet. Sorry, the number 6 is there. So I want you to run the analysis using Q4, Q8, Q9 and all reduced integration elements. Q4R to be precise, 8R and Q9R. Don't complain, I made all the code for you already. You just need to go through and use this code to play with your little finite element analysis. I want you to use all of these to analyze the beams, and the point is that we have different two different cases, right? We have the short, or let's say deep beam and deep beam and slender beam. That these are your homework that you finish already. You turn in, you receive it back. So there were two aspect ratios of the beam. The aspect ratio is given by the span to the depth of the cross section. So these two aspect ratio for the slender beam, if you recall, at that time slender beam is very well predicted. The behavior, the response is very well predicted by the Euler beam's element. Okay, that's the first thing. And how about the Timoshenko beam? iPad. Oh, sorry. Yeah, I forget. Yeah, come back to this. Here. Sorry. Yeah, just keep talking and I don't know where am I. So the slender beam is well predicted by Euler's beam theory. Yeah? And that is taken care of by Hermite shape function. Euler beam theory using that 5/384 WL to the 4th over EI. That is a good tool to compute the that is the exact solution from the Euler's beam theory. And one problem that you confront with at that time, and that's why we need to use the reduced integration for Timoshenko beams, is because we have the shear locking in the Timoshenko's beam, and there were two possibilities to come across that problem, which are: the first, you use the smaller discretizations, and as the discretization is getting smaller and smaller and smaller, and you do not overestimate the shear deformation in the Timoshenko beam. If you just have a few elements, your shear evaluated from these few elements gonna be excessive. If you combine many of these in order to get the same element size, you find that shear strain level in small element size is much smaller than the large element size. So this is the issue that depends on the element size. And the identical thing is going to happen also for the Q element, because you are going to discretize the Q elements, and the discretization of Q element is more painful than Timoshenko beam element, which is just 1D element. 1D elements, okay, you discretize 100 of small sub pieces, it doesn't bother you. That is a cheap element. 100 element, you just end up with around 202 degree of freedom. That's a piece of cake. Matrix is very easy to solve, so you don't see the cost for the discretization from maybe 10 to 100. That does not bother you. But when you talk about Q element, you discretize in both directions. The value, the number of degree of freedom is gonna increase exponentially. So sometimes you will need this reduced integration. And the same thing, so the shear deformation, if you have the element which is big like this in comparison with the small element that might deform and adds up to be like the big one, so in the smaller one you don't overestimate the shear. By the way, guys, I think one thing I haven't done yet, so I have to jump back. Let me check. One thing that I haven't done yet is the reduced integration, right? So yeah, so it's a reduced integration. Look at this. The B mat is just made for one kind, so this B mat includes both behavior in the shear and in the volumetric part combined together. I talk about the reduced integration in one class already, that the K is going to be the K for the volumetric part and deviatoric part. This K come from the B, which includes 0, 0, 0, 0, something, something, 0, 0, 0, 0, something, something. Okay, this is epsilon x, epsilon y, gamma xy. Okay, so this is the B for the shear. Okay, you use this, and another B will be partial derivative of phi with respect to x, 0, 0 partial derivative with respect to y, and then 0, 0. And this thing repeats. This is the B for another part. This part here will be fully integrated, whereas this part here will be reduced integration. You will not apply the reduced integration in this part because it is not the problematic part, and if you reduce integration, then you're going to end up with a problem. So full integration is going to be conducted here, reduced integration for the shear part, let's say. So you combine these two. Now, sorry. Okay, I come to here. Okay. Let me cover it again. Okay, will be broken into volumetric part and deviatoric part. This volumetric part comprises partial derivative of shape function with x with y, and it does not have the entries here. It's 0 because this is the shear component associated with shear strain components. Whereas the deviatoric part, you have 0, 0. You have only just the components, the entries that are associated with gamma, x, and y. So you got the B for shear and B for the volumetric part. You end up, you can do it. Well, let's see. Do I need to do it for you, or you can do it for yourself? This one will be evaluated. Okay. Yeah, it needs the evaluation at a different time. I mean, inside the numerical integration, should I leave this for you to do, or should I help you do it? I think I'm gonna have to help you. So the homework might be done in the just to find the zero energy mode first. This is going to need the coding, and the coding is gonna be in here. I'll bring you here. This part here, I got to break it down. So one part of the code will be for I'll just need some parameters, and that's gonna involve with the input. Let's do it. Actually, it does not take so much time. So everything we establish, we get the DMAT, we get the KELE, element XY, we get XY. Now this is the full integration. We have NINT, and it doesn't break into two parts. So yeah, this is going to be a lot of things going on here. First, if we actually need to add one more parameter in which one? Let's take a look at the input file. It's not going to be inside the coordinates. It's not going to be in the nmap. So I think it has to be in the EPRP. We need to add up the element. Each individual element can be fully integrated or reduced integrated. If do we need the mixture of many elements? Well, RINT, reduce integration. This is going to be the option. RINT, where is it? It should be here. Home. RINT. Reduce integration. 0 for no, 1 for yes. So if RINT is equal to 0 without this is associated with full integration. Okay. And then all these things, the loop over the Gauss point is going to be nested inside here, and else if RINT, well, if it's not full integration, that's gonna be just the else, right? Else, or we want it to be explicit. RINT is equal to 1, which means yes, it is the reduced integration. Indented code. How much time did we spend so far? Start from what? From 7:20. Okay, fine. I know you stay up late. You don't sleep. Meh. Why is it just indent? Okay. So we have full integration there. If we don't go for full integration, then we're gonna need the reduced integration. Reduced integration is going to happen here, and you're gonna have two parts of the code, right? Format indent code. Oops, what is no indent code? Okay. And then I if first. If. Okay. And that is it. Plugging in is not going to be altered. This part here is going to come in. Now, the reduced integration, we're gonna have two parts. Loop over Gauss point, yes, but what is this? This is the volumetric part. And the another is the deviatoric part. Volumetric part will be full integration, fully integrated. So of course NINT is there, NINT is there because it is a full integration. C is there, eta is there, BMAT is calculated, so I assign DMAT V equals to zeros 3 by 3. Likewise, the mat deviator zeros 3, 3. The mat V 1, 1 equals to 1 like this equals to D mat 1, D mat volumetric part number 2, row number 2 is equals to D mat 2, and D mat deviator 3, 3 is equal to D mat 3, 3. Okay, that's it. So you can see that I just give the 1, 2, 1, 1, 1, 2, 2, 1, 2, 2 to the D mat V, and the D mat D is 3, 3, only non-zero at 3, 3 is equal to the 3, 3 part. And then now we are talking about volumetric part, so I just cut it here and paste it there. What we need to look at to fix is D mat volumetric, that's it, and then deviatoric part I'm gonna copy off this and paste it. Now it is going to be the reduced integration -1 here and -1. Of course, the C and eta this is not fun. I have to prepare it. Okay, stands for reduced integration. That means I got to come up here. C eta R and WGHT R equals to Gauss NINT -1. If RINT is equal to 1, and if it is 0, then it will be just that one. If it is not 0, then you're gonna have this part also. Indent code, and yes, okay. So this is initialized. You can get them. Why do I need to get it? Like, oh, okay. So just one thing. Okay, C is taken. Eta is also taken, and it is perfectly fine because this is for the calculation in here. So element type, element XY, DN, DZ, yes, okay. B mat, just go ahead, and D mat no dot volumetric but deviatoric part is going to be obtained, and C eta are already taken care of. Okay, they took the reduced integration coordinates in there already, so it is okay. All calculations taking place. The only thing is that the weight turns out to be weight R. Okay, because you use a different weight, the number of integration points is reduced and the weight is changed as well as the C and eta. Let's take a look here. The K Eli is the summation, okay, from this point and down to here, because it's just accumulating everything up and it is reset over here, so it makes sense. Every time it starts, for each element it resets, and then okay, if it is full integration, it's gonna work, or if it is a reduced integration, it's gonna work as well, because it's gonna sum up the part for the volumetric first, and then it comes to deviatoric part. Okay, the numerical integration is carried out differently for these two, and that's it. Okay, and yes, now we have one more thing to fix. I think you will need the here. So NINT and comma RINT has to be there. If the RINT is going to be there, spelling line 27, thank you, Gauss, GAUSS, thank you. GAUSS, yes, thank you, Sivaram. So what next? RINT, okay, RINT. So I need to rect match, right? And read rect match. Yes, I gonna need this to include some lines, and that should be number of integration points, and then it gives the dot home, copy, and there it is, reduce integration option, reduce integration 0 for no, thank you, and 1 for yes please, and I leave the dot there. Save it. So this is going to spare this space, and you will need to give the input either 0 or 1. And after the rect match, I got to come across input read, and the input read is going to have RINT, and the RINT should come nodal point mapping. Number of integration point is here. I come after reduce integration, reduce integration option. It's got a first FID, and I will reduce integration, and just that. Okay. Alright, so this is just a minor adjustment. RINT in place, then it's gonna work. RINT equals 0 is nothing different, it's just go here. But if it is not like that, then we got to break the rigidity matrix into two matrices, the volumetric part and the deviatoric part. Volumetric part, deviatoric part. Okay, we come into volumetric part, integration over two axes, numerical integrations carried out, sum up here. KELE is not reset, it is carried over to here and accumulate the values in to here. So Jacobian is computed from C eta from reduced integration. Weight is also from reduced integration. Okay, save it. Should we run it? Okay, why not? So the first thing we got to do is the rect match. We can try smaller problem. Okay. Option 0 or 1, right? I don't. Option 1 or geometry visualization 0. Okay. So I just need option 1. Element type Q8 NX 2 NY 2 HX, make it NX and Y. NX make it 6. Okay, NY 2 HX 2 HY 2. File name match 6x2 .txt. But boy, slow. Just this. Why it takes so long time? Come on. Oh, there it is. And then I have the rect 6 by something. Oh no, I don't get it right now. I have it, and then I come to the number 2, and the 6x2 is popping up, and no, I don't need this one here. And we'll see. Element type, number of nodes 53, elements, number of elements 12, of course. And nmap is provided, EPRP, element property has to be provided. We're gonna need the Excel, right? Okay, and that is going to be how many? 12 elements. Element property, what do we have in the element property so far? Gonna see the test 1. Which one? This is test. Oh no, it is not there. Test 0. Element properties. Okay, this is not the complete one. I know. This is gotta be, yeah. I don't remember. I made all this code, but I don't remember anything. Okay, so elastic modulus and Poisson ratio. We're gonna make it out of a Excel file. So elastic modulus, some silly number, and 0.2. We need 12 of them. Row number 12. That's it. Copy and come back here, paste. That's it. Element property, integration points. This is QS. You need 3 in each direction. Reduce integration. Yes, please. Number of essential boundary condition. We have where? I just put it number 2 and number 33. Number 21. 21, 2 degree of freedom, restraint, and 33. So in total number is 3. List of restraint DOF. 21 is 41 and 42 and 33 is 66. Okay, we restrain only Y degree of freedom. Number of force boundary condition. Force boundary condition, just make it okay, 1 2 3 1 2 3. So make it at 47, just 1 point. Just lazy. 47 multiplied by 2 is 94, and we need like minus 10. Okay. Oh, number of tests, and this is just 1. And save it, and main update is there. So there you go, main UPD. MAIN UPD of match 6/2 .txt. What is this? This does not look good at all. What is this? Answer equal to 1 1 1 1. What is it? Patch size x, y, z must be equal. It doesn't plot anything. What is going on there? Answer equals to what is this? What is answer equals to 1 there? Enforce. Oh, I think I must have missed something. Close. And this is not accumulate. Is there anything wrong in the input read? Force looks good. Reduce integration, number of restraint, list of restraint, degree of freedom. What is this? Number of integration 3. Reduce integration, yes. Boundary condition 3. Number of force 1. What is answer equal to 1? Did I miss anything? So it's not about the input read. Wait. Gauss NINT minus 1. Why do I have this? I think the suspicious part is answer equals to 1. Must be equal. Patch size of x, y, and z must be equal. Okay. Let's try this first. 6 by 2. Let's make it 0. It should work, huh? This is the old thing. Now, okay, modify the code and something happened. Patch size of patch as line something, main update at line 444 column 7, fill at 138 column 25, main update at 444 column 7. Unbelievable. 444. Okay, column 7. Okay, field has a problem. Why is it having this problem? So the value of the closing node, temp x, temp y. This is what? Color plotting for Q8. If PEXX. Why? Color plotting for Q8. Okay. Here is gonna be the problem. If element type is greater than 4, this is going on. JI to 8. Yeah, I just want to fix the bug before I go to bed. Store the values of closing node. Okay, TEXX, fill temporarily XY. What? 444 TMXY. The thing is that now we have less integration point. The shear will be evaluated from 1 and okay, but the error is like TMXX, TMXY, and TEXX are not in the same dimension, right? So if this is n strain n map. The dimension is given TMXY. Is it because of the new code, or is it like not working? It used to work for Q8, the old version works. This is 9, which is okay because we need 9 coordinates in order to close the loop. What? Line 444, fill TMXY, TMXY, and TEXXXX. PEXX is equal to 1. Where is the PEXX? Where is it? Yes, they are all equal to 1. And I don't understand that thing. But that one doesn't pop up anymore. Must be equal, right? 444. I just wish I could get a good night's sleep. What is that bug? So the values, okay, just concentrate. 444 tmxy. Tmxy is where? Tmxy is 0. Yes. And texx is 9. How come? Tmxy is equal to this. And seriously, what? I think we used to plot the Q8. Okay, fine. This is easy then. Tmxy is going to be 9 2, right? And then at the end of this, tmxy of 9 comma is equal to tmxy of 1 comma. That's it. So now the dimension is consistent, but I just wonder, I think this point must be resolved before. Okay, just add the line. So tmxy, it shouldn't be the issue. Okay, texx. Okay, let's try it again. Or maybe it's the bug that we never know. Go ahead, guys. Go ahead. Plot. Okay, now there you go. It's the ugly thing goes. Okay. Boy. Well, anyway, I know this is stupid. Yeah. So this is something stupid. Well, haven't we done anything with the 64 by 16? What is it? What is that element? Q4? Oh, well, there you go. It is Q4. So we have the Q4 stress plot verified, but we never really get the Q8. Okay, fine. But now the point is that TM, what is this? What is this, guys? What is this? What is TTMXY? Come on. Okay, alright. Okay, it was supposed to work this way. Delete this, and we're supposed to be TTMXY. Okay, right? Because it is transfer YTTXY. Why? It has no reason. 1 2 3 4 5 was supposed to be T. What is the TTXY? Huh? TTXY. That is a tall XY. And why do I take it? Well, okay. Control F. Phi TTXY. Replace it by TMXY. Phi next. Replace. Got it. Okay. So TTXY is just a Tor. Okay. Alright, guys. So I think it works now. Temporary XY is transferred and then TTMXY, okay, makes sense. It has to be TTM and TTMXY. Okay, it is TTM. So that's a bunch of this to fix in order to get the dimension match and TTMXY. Okay, that's this. And then it plots out everything hopefully correctly. Then let's call it again. There it is. Yeah, okay, I think now it makes sense. Stress, XX, compression, tension. We have just a few number of elements, so here is what you get. The part that plots the deformed shape is not working as I wish here. So let's see. You guys still alive? Yeah, you are not dying yet. I can continue. I think I lose the sense of time when I teach in the night. So there is no class after this one. And there it is. Deform mesh plot. You have the exaggeration factor over there. Element type equal to 8. Element type equal to 9. Okay. So what do we have to do? Plot is here. Hold on. And just like this one, hold on. Yeah. That's the hold on. Yeah. Save it. I'd like to see the deformed shape a little bit. Do it again. Okay. And I didn't put the axis equal plot. Boop. Axis equal. Save it. The other things are given out. I just didn't drag it to this screen. Well, close it all down. And this one is not nice one yet. Okay, I get what I want now. There it is. Okay. So we are very happy to have this thing works. This is what without reduced integration, right? Let's see if we reduce integration. So mesh, this is reduced integration will be changed to yes. Save it. And if it is if it bugs again, I will just stop here. I don't know if it's gonna bug or not. And why? Okay. Ew. This is a bad thing. Answer equals to 1. I don't know what is. What is this answer equal to 1? Okay. Reduce integration codes work. I cannot say explicitly that it works, but it gives something out, and it doesn't look terrible. So let me see. What is the reason why we obtain the number 1111111 out of there? So it will not be caused by this part here. Else, do we need like do we need this? Is it necessary? What else could give still 1? We have this close down. No, this is not going to be the case. Close, semicolon is all there. So it doesn't make anything. What? C, eta, this close down, close. Is it supposed to be like this? See? Hopefully the reason for so that one is because the point behind the else. There it is. I sort of ran out of energy a little bit, and I don't drink coffee in the night. That's the point, guys. Then you should compare the result obtained from reduced integration and the full integration. Let's see. 0 drops down to somewhere around minus 0.87. This problem might not be so sensitive with shear, and the shear locking might not be expected. I don't know. I didn't run this sensitivity analysis, but let's take a look. If it is sensitive to the shear locking, then the vertical displacement shouldn't be close. So I'm gonna go for the full integration and see what we're gonna end up with. Alright, this is somewhere around 0.87. Okay, so 0.87, and call this again. Now it is the full integration. Actually, you can extract the displacement vector, but it's just lazy. Let me just get the deformed shape. Roughly it is about 8.7, 8.3 or 8.7. Okay, got to check into the numbers. Okay, but it looks still so close. So the locking might not be the case for this problem. Alright, now it works, but you will investigate further into this matter. Please do the homework, and if you bump up into any issue, then you have something to talk. I will arrange one Zoom meeting, so you can ask questions if you have, and do not send me the separate email or like the personal email, like from you to me, not to the class, because I do not want to answer individual answer. If the question is coming, then I got to open this to the whole class to get exposed to the same information. So asking during the Zoom, well, line number 68 turns out to be else if. Why 67? 68? else. Oh yeah, if I say RINT equals to 1, right? Else if, but it doesn't change anything. I think it shouldn't change anything. Else or else if, then it yeah. And then that's why RINT turns out to be, oh, okay, then that's interesting. That is like having the else, and then once it is else, then the RINT is adjusted to be 1.1. That means the condition used to be 0, and then now it is changed to 1. Okay, good point, Navindra. Let's take a look. Let's try. So now we are going to expect the if it is not, because previously the full integration turns out to be reduced integration at one point when it comes into the loop, and the RINT is then adjusted. Okay, so this is what, 0.83. This is probably the real full integration, 0.83. Yeah, maybe again, extract from the displacement vector should be the case. That would be better for the comparison. Okay, this is interesting. Very good for the line number 68 mistake pinpointed by Navindra. I'll upload this. I will also upload the video tomorrow. I don't have energy to edit the video further tonight. Alright, so I guess this lullaby is going to give you the good night's sleep, and I will just finish the class over here. Alright, see you tomorrow in the advanced steel structure. Have a good night, and I am still waiting for the email from you if you still have something to send me for the confession. Alright, bye bye, have a good night.